Polyols are versatile compounds with multiple hydroxyl groups that play a crucial role in various industries, particularly in the production of polyurethanes. These compounds are essential components in the manufacturing of foams, coatings, adhesives, sealants, and elastomers. Understanding the different types of polyols is vital for selecting the right material for specific applications and achieving desired product properties. Polyols are reactive substances, usually liquids, that contain at least two isocyanate-reactive groups attached to a single molecule. There are wide varieties of polyols, but most used fall into two major categories: hydroxyl-terminated or amino-terminated. Polyols, or macroglycols, have a profound effect on the properties of the finished polyurethane. While associating the properties of the polymers with the urethane linkage, the structure of the polyol has a direct bearing on both processing and finished properties of the polyurethane polymer. In fact, the majority of the linkages found in polyurethanes are derived from the linkages found in the polyol. Thus, if polyether-based or polyester-based polyols are used, we obtain polyether-based or polyester-based polyurethanes. There are four classes of polyols, namely polyether polyols, amine-terminated polyethers, polyester polyols, and polycarbonate polyols. Polyether polyols are produced through a polyaddition reaction involving a starter, a compound containing active hydrogen groups, and epoxides such as ethylene oxide, propylene oxide in the presence of a catalyst. These materials are the products of a reaction between a simple starter molecule, also called initiator, such as ethylene glycol, propylene glycol, glycerin, pentaerythritol, trimethylol propane, sucrose or sorbitol, and a cyclic ether such as ethylene oxide EO, propylene oxide PO, mixtures of EO and PO, or tetrahydrofuran THF. The functionality of the resultant polyether depends on the functionality of the chosen initiator. Thus, if the initiator is a diol, the resultant polyol will have functionality of 2. Conversely, if the initiator is a triol, the resultant polyol will have functionality of 3. Polyether-based polyols produce very high-quality polyurethane foams and elastomers. Among the most important polyether polyols are the poly-BD, polytetramethylene ether glycol, PTMEG, polypropylene oxide glycol, and polybutylene oxide glycol. PTMEG, generally synthesized from furfural, is of special interest as a reactant in the production of hydrolysis-resistant polyurethane elastomers. It also offers excellent flexibility and impact resistance. Amine-terminated polyethers, also known as polyether polyamines. These are based on polyether polyols, in which the terminal hydroxyl groups have been replaced by primary or secondary amino functionalities. Polyether polyamines, PEA, are versatile organic chemicals with ether and amine groups in their structure, featuring a polyether backbone, like polyether or polypropylene oxide, with terminal amino groups, giving them low viscosity, low vapor pressure, and excellent solubility in many solvents, making them crucial as flexible epoxy curing agents for tough, impact-resistant coatings, adhesives, and sealants, as well as components in polyurethane systems. Polyester polyols are typically synthesized through the condensation reaction of dicarboxylic acids or their derivatives with glycols. Polyester polyols offer several advantageous properties, including excellent solvent resistance, superior adhesion to various substrates, and enhanced mechanical properties compared to their polyether counterparts. Polyester polyols are polyalkylene glycol esters, such as polybutylene, terephthalate, or adipat, or caprolactone polyesters. Polyalkylene glycol adipades are prepared by condensation, polymerization of the alkaline glycol, and the corresponding diester or diacid. For example, 1,4-butanidiol plus adipic acid will form polybutanidyl adipati. 1.6-hexanidiol, neopentyl glycol, butanidiol, ethylene and propylene glycols, glycerin and trimethylol propane are the most important glycols and polyols used in the manufacture of polyester polyols. The most important acids in polyester polyol synthesis are adipic acid, azelaic acid, phthalic anhydride, isophthalic acid, and dimethylol propionic acid. The condensation chemistry is carefully controlled to ensure that these polyols contain terminal hydroxyl groups. Caprolactone polyesters are prepared by ring-opening polymerization of caprolactone monomer with a glycol such as diethylene glycol or ethylene glycol. Caprolactone polyols are used in those applications where better hydrolytic stability is important. Castor oil is a polyester-based polyol with good hydrolytic stability. Castor oil-based polyurethanes are frequently used in the production of casting compounds. Polycarbonate polyol is a type of polyol containing carbonate groups in its backbone, used in the production of polyurethanes to impart properties like high impact resistance and flexibility. Polycarbonate polyols, such as poly-1,6-hexanidiol carbonate, are prepared by condensation of phosgene or alkaline glycol carbonates. For example, dimethyl carbonate with alkaline glycols such as 1,6-hexanidiol. As in ester chemistry, this chemistry is also controlled to ensure that these polycarbonates contain terminal hydroxyl groups. Furthermore, polycarbonate polyols are based on carbon dioxide, CO2, and sequester CO2 directly in their backbones, enhancing the sustainability of polyurethanes. Polyols, essential in polyurethane and polymer production, are divided into polyether and polyester categories, each with distinct properties and applications. Polyether polyols like PPG and PTMEG, including their copolymers, are valued for versatility and cost efficiency. Polyester polyols, encompassing aliphatic, aromatic, and mixed acid varieties, offer superior mechanical strength and solvent resistance. Selecting between polyether and polyester polyols depends on specific needs such as hydrolytic stability, mechanical properties, chemical resistance, and cost, critical for developing tailored, high-performance products. Ongoing advancements in the polymer industry are expected to introduce new polyol types and enhancements, expanding customization options and optimizing performance across diverse applications.